So welcome back to my lectures on groups, rings and fields. Our next topic is on some non-commutative examples of rings. Non-commutative examples. So far we've been discussing about commutative rings, meaning the multiplication is commutative. So in this section what we are going to do is to give you some examples on non-commutative ring where the multiplication is not commutative. We have done this, just one example, the ring of matrices, n by n matrices over real numbers. So this is a non-commutative ring. The multiplication on n by n matrix is not commutative. So we are going to give actually three different examples other than this ring of matrices. So the first example is we'll start with an abelian group. Let G be an abelian group. Okay, an abelian group. Then consider the collection of all homomorphisms from G to G. By the way, this collection is called, a homomorphism from G to G is called an endomorphism. This is not isomorphism, because for isomorphism this has to be bijective. This doesn't need to be a bijective. Could be any homomorphism from G to G. So let the collection of all endomorphisms on G be E and D of G. So we have the elements of the ring which we are going to consider. Those are the endomorphisms on an abelian group. So we need to define two operations here: addition and multiplication. And it shows that this addition and multiplication follows the axioms of a ring. And once we are done with this, we will find an example of a group G where the endomorphisms with these additions and multiplication is not commutative, and that is the first example. So the addition is, this contains endomorphism or homomorphism from G to G. So we take two endomorphisms from G. So let phi and psi be two homomorphisms from G to G. Then phi plus psi of G or G is equal to phi of G plus psi of G. There are a lot of verification needed here. I am not going through each and every verification. These are all very straightforward verifications. First thing we need to prove is that with this addition, this endomorphism is an abelian group. Even for non-commutative examples, the addition part is actually an abelian group. So we need to show that, or you can say, I'm going to write, I'm not going to show this, verify that we'll call E, comma, plus E is the endomorphism on G, or you can say EG, endomorphism on G. With this addition is an abelian group. And what is the identity of this group? With the identity as the zero homomorphism. Zero homomorphism means every element of G is mapped to the additive identity of this group, and that map is the additive identity of this group. Yeah? And inverse of phi is minus phi, defined from G to G by minus phi of A is equal to minus of phi A. So this is an abelian group. Okay. Now multiplication on the collection of endomorphisms. So let psi and phi and psi belongs to E end of G. Then phi times G, sorry, phi times psi is equal to phi after psi, and that is also from G to G. Okay, so this is the definition of multiplication. So we need to prove that this is a ring. We need to show that the multiplication is verify the multiplication is associative and is distributive over addition, which is a simple process. I'm not going to verify that. So with this, the endomorphism, collection of endomorphism on G plus with the addition and the composition is a ring. Now what we are going to do is we are going to give you an example of a ring where the multiplication is not necessarily commutative. So here we are going to take G as the additive group of Z cross C. This is an abelian group, so we have to start with an abelian group, and we are going to take all the endomorphisms on G, and we are going to define two endomorphisms that will not be commutative when you consider the multiplication. So define phi as phi of phi from G to G by phi of m comma n is equal to m plus n comma 0, and psi from G to G by psi of m comma n is equal to 0 comma n. Now we'll see phi after psi of m comma n, and that is equal to phi of, this is going to be 0 comma n, and that is going to be n comma 0. And psi after phi of mn is equal to psi after phi of mn is m plus n comma 0, and psi of this will be 0 comma 0, and that implies phi after psi is different from psi after phi. So this is a non-commutative ring. Our next example on non-commutative rings are group rings, or structures called group rings and group algebras. These groups, rings and group algebras are not necessarily a non-commutative ring always, but we can find non-commutative rings in these examples. So let us define the elements of the ring. So let G is equal to Gi, I belongs to some index set, be any group, not necessarily an abelian group, and Rb a commutative ring. Then consider the collection of formal sums of elements from G and R as sigma I is equal, I belongs to I, AI, GI, where AIs are 0 for all but finite number of AIs. for a number of AIs. This cannot be an infinite sum, it is a finite sum. Even though G contains infinite and R contains infinite, we are only considering finite sums. So these are the elements of the ring which you are going to consider. Now we need to define two operations, binary operations, addition and subtraction. Addition is, we'll take two elements like sigma I belongs to I, AI, GI plus sigma I belongs to I, BI, GI is equal to sigma AI plus BI, GI. If you want to prove that this belongs to the collection, it is easy because here we have only finite number of AIs that are different from zeros, and here also there are only finite number of BIs that are different from zeros. So this is actually the combination of these two are elements coming from R. So this plus is actually the binary operation, the addition of R. Okay, so this will be finite number of AI plus BI, which is different from zero. All others will be zeros. So definitely this belongs to the collection we are defining. So I'm not going to prove that this collection along with this addition is an abelian group. Okay, so we are going to say that the denote, we have to do this, denote this collection of elements as RG. So verify RG with this addition is an abelian group. We are going to do some examples on this. So we'll be clear how we are considering this elements. And multiplication is actually by sigma AI GI, I belongs to I, sigma I belongs to I, BI GI is equal to, or B, you can write it as Bj, this is J and this is J, is equal to sigma I belongs to J, I belongs to I, then sigma GI or GK is equal to GI times GJ. Here AI BJ times GK. I'll explain you what this means is, if you take two elements, let us say A1 G1 plus A2 G2 times B1 let us say G3 plus B2, let us say B4, then we are multiplying like this: A1 G1 plus A2 G2, B1 G3 plus B2 G4. So this is A1 B1, G1 G2, G1 G2, and that is our GK. G1 G2, this is G1 G2, that is GK. So when you multiply, if you have another G1 G2, you write it under this, okay, plus A2 B1 G2 G3. This is our GK again. So whenever you have a G2 G3 in this combination, if you multiply, then you add all this together. You can add this because this is coming from R, a commutative ring. So you have an addition defined here, and that is what this says. We will do some examples, so this will be very clear. So with this, we need to verify this is a ring. So verify RG with addition is an abelian group with identity. What will be the identity of this? The identity of this will be 0 times any element of Gi. This is the identity because this is a finite sum. So if you add sigma I to I, Ai, Gi plus 0 Gi, and that will become Ai plus 0 Gi sigma, and that is actually nothing but Ai Gi. So this is the identity of the abelian group, and the inverse of sigma I belongs to I, Ai, Gi will be sigma I belongs to I minus Ai, Gi. Because when you add these together, you will get this. Of course, we need to prove the associativity and all of that. I'll leave it to you. And we need to show that multiplication is verified, multiplication is associative and distributive over addition. When we do the example, this part will be very clear. And when will this become a non-commutative ring? When G is a non-abelian group then Rg plus dot will be a non-commutative node, a non-commutative ring. Why? Because see 1 dot G1 belongs to RG. 1 dot G2 belongs to RG. Okay, and I'm choosing G1 and G2 such that choose G1 and G2 such that G1 is different from, G1 G2 is different from G2 G1, because this is a non-abelian group. You can choose like that, and that implies 1 G1 times 1 G2 is different from 1 G2 times 1 G1, and that implies RG is non-commutative ring. Now that is actually, so this ring is called the group rings. This ring is called group ring. Is made from a group and a ring. G is the group and R is a ring. And when R becomes a field, when R is a field, then RG is a group algebra. Even if R is a field, RG could be a non-commutative ring because of this fact. If you take G is a non-abelian group, then RG is always a non-abelian group, non-commutative ring. Okay, so when R is a field, it is called a group algebra. Normally, when you say it's a field, it's called F is a field, then FG is a group algebra. So this is an example of a non-commutative ring. Now let us do an example using this group ring and group algebras. Okay, so let G is equal to EAB be a cyclic group, meaning A is generated by either B or A. Okay, and okay, that is fine. Then find or compute the following. Compute the following in Z5G. Z5G. So this is our R and this is our G. Okay. So our computation is like this: 4E plus 3A plus 0B plus 2E plus 4A plus B. This is one. And second one would be probably, let us take 2E plus 3A plus 4B to the power of 2. Okay, we'll do both of this. These are not, see, when you consider 4E, it is not a multiplication of 4 times E. This is an element in C5G. So first we need to add these two. So adding is just like this: 4e plus 3a plus 0b, 2e plus 4a plus b. Plus b means this is actually 1b. We always write it like this, 1b. So this is actually 1b. So we need to add like terms. So this is actually 6e plus 6e. Okay, so this is coming from, all are coming from z5. None of the coefficients are above 5. All are coming from c5. So 6 means e. So 1e plus this is actually 2a plus 1b. So this is equal to 1e plus 2a plus 1b. We need to write it like this. We cannot reduce further. This is not e plus 2a plus b. Okay. Now let us compute this one. How do you do this? Again, 2e plus 3a plus b, 4b, by again multiply 2e plus 3a plus 4b. So how do you multiply this? You multiply just like you multiply the numbers. So 4e, this is not 4e square, 4e only, because you are only multiplying these two. 2e times 2e is equal to 2 times 2e. That is how you are multiplying it. So this is going to be, because there is no e square. Okay, so here this is going to be 6ae, right? So this is going to be a. 6 is actually 1, and this is going to be 8. So this is going to be 3b. Before that, I need to write down the multiplication table of this. This is actually EAB, 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 AB. A square is B, AB is E, BA is B, BA is E, and B square is A. And that is how this is becoming a cyclic group. Because A is equal to A square is B, and A cube is equal to A square times B, and that is B. A square times A, A square times A, and that is B times A, and that is E. And that is how you get this cyclic group. So A square is B. So when you multiply here, this will be definitely 6a. That is A. This will be 9a square. 9 is 4. A square is B. 4b. And this is 12 is 2. 2ab. AB is 1. AB is 1. So this is actually going to be 2e. So this is going to be 8b. That is 3b. This is going to be AB is E. So this is 12. So 2e. This is B square 16. That is 1. So 8. So this is going to be 8 that is 3e plus 3a plus 0b. So this is going to be 3e plus 3a plus 0b. Okay?